So, hello, I'm Radim Krčmář. I work for Ventana, where we're developing high-performance RISC-V, and it's an emerging architecture, and we also want to have confidential compute because, well, the Linux is kind of big and not trusted. And one of the confidential solutions is pKVM, which you might know from ARM. And basically, the idea is to have the same design as ARM, just to run it on RISC-V. And because RISC-V doesn't have any hardware-defined solution for confidential compute, we definitely need to do something in software. And one of the options is to make it in firmware, but, well, we don't like firmware that much. And if you then move to the upper level, it's operating systems and Linux. And pKVM has, on ARM, shown to be quite nice design, giving flexibility while still providing a decent amount of confidentiality. And one of the important designs in RISC-V is first ask the question, how does ARM do it? And, well, then we usually need to have something similar. So on the RISC-V, the isolation between Linux and the confidential VMs is slightly different because the basic privilege levels are M, where the firmware is, then S, where Linux, and U, where you run your applications and VMM. And for pKVM, we will be using the hypervisor extension, which renames the S and U to HS and HU, and adds two more modes, the VS and VU. And similarly, how the firmware can control the HS mode and all the modes above, then the new HS mode has the control over VS and VU. So there are environment controls, state controls, delegation, and counter controls. All of this to make sure that the virtualized modes can't access the protected registers and processor state. And if you remove the H letter and put M, it's basically the same tools that the firmware has. So it doesn't make that much difference on when this confidential hypervisor is going to run. So MMU is a big part of the isolation. And here, similarly, we have three CSRs, control status registers, where the HS mode has the SATP, where it controls the page tables for itself and for its applications. And when running in VS mode, there's VASTP, which does basically the same for VS and VU. And when running in VS mode, the operating system still thinks it's accessing the SATP. It's just virtualized into VSATP in hardware. And then the HS mode, it has the HGATP, which controls what the virtualized mode can access. And it's the main tool used to isolate Linux from the confidential VMs, because our goal is to execute in HS mode only the trusted hypervisor, the pKVM, and in the VS mode, there will be Linux, and in VS mode, there will be also the confidential VMs protected from itself by the HGATP. So how it's going to look, because pKVM and Linux start as a part of the same binary. They're compiled at the same time, and they're booted and laid out in the memory. And when we want to split it, then pKVM is the only one who should remain in the higher privileged HS mode. So we don't want to accidentally execute nor access the untrusted code from the original Linux. And then we just unmap it through the SATP. But VS Linux, the Linux in VS mode should continue running basically as it did before. So the pKVM will virtualize it, and it's going to be one-to-one mapping from how it was before we split it. It's just that the pKVM code, nor data, nor some of the I/O devices that would break confidentiality can be accessed anymore. And this is going to be done through the HGATP, which will just return an access violation should the VS Linux try to do it. And there's also the I/O HGATP, which is a part of IOMMU, to do the same isolation for devices. Because when Linux boots in HS mode, it configures the devices to communicate with itself in HS mode. But now that we are moving Linux into VS mode, the devices are still communicating with HS mode. And it's pKVM there, and it doesn't, pKVM there doesn't really care what the interrupts and the Linux wants to communicate with. So we could handle them and just forward them in software, but the IMMU allows us through the M6, which is basically a page, and the device is configured to write to a page. And from this page, then the interrupt gets delivered. And because it's just a page that the device writes to, we can change it into another page and say that because the CPU has one page that says, well, if a memory write happens to this page, then this will get delivered as an interrupt to HS mode. And then there's for each CPU another page, which if it gets written there, it gets delivered to a VS mode. So we assign one of the VS modes for VS Linux and reconfigure the IO and GATP page tables to just directly inject the interrupts into VS mode. This way, the pKVM doesn't have to handle the interrupts for Linux, and devices still continue to work. So this is basically how the split happens. And to go back to ARM, there are deep parallels. Like we still boot the kernel image, which contains both Linux and KVM, and because we need the trust, the bootloader needs to verify it. And the kernel isn't entered at EL2, it's HS. And because HS is the mode where pKVM is going to continue running, we don't need to install the subvectors anymore. As in ARM, you need to iterate to EL1 because that's where the operating system runs, but operating system runs in HS normally on RISC-V. So we don't need to install anything and iterate that early. We need to reserve the memory for pKVM because we still need the page tables for isolation. And then we don't need to have the temporary page tables because we just split in when everything is correctly prepared. But we do need the stacks and per CPU pages. And then the pKVM init hypercall, which does the setup, isn't really needed because we can all do it in HS mode. So we recreate the page tables for the host to properly isolate that pKVM can't be accessed from the VS mode, nor that pKVM accidentally executes or accesses untrusted code. And then we do the same for devices, configure some of the HCSRs, and then just the VS Linux continues running basically as it did before, just it's not a host anymore, but it runs as a guest. And then the only way how the Linux in VS mode can communicate with pKVM is through hypercalls. And hypercalls on RISC-V are using the equal instruction, but it's not only hypercalls that are used to communicate with pKVM. The equals are used for many things like writing to a console or setting up a PMU, shutting down the machine, or onlining, offlining CPUs. And some of them, for example, like writing to a console, there's an equal that says, well, from this address, write this string, which is 0 terminated array of bytes into some physical console. Well, and if pKVM, it doesn't know how to do it because it has no devices of its own. So its only way to implement the equals is to then tell M mode, which is below it, to do the write. But well, if now we just blindly forward the request from Linux into M mode, it's possible that Linux would access the confidential memory, which would break confidentiality. So we in pKVM need to intercept and understand all the equals to triage if they're safe or not. And if they're safe, we forward them to M mode. And this adds quite a bit of complexity because RISC-V tries to do as much as it can in software. So the equal interface is growing to be big and featureful, and only just checking if an equal is safe is going to require a lot of code in the trusted hypervisor. And the more code you have, the less trusted you are. So it's still an open question how to solve this. The easiest way would be to convince Linux, well, don't use equals, but most of them are kind of useful, like changing frequency on your CPU. And then I think we'll end up with having pKVM actually implement and check all the equals eventually, which hopefully we'll try to make it better, but this is looking to be the only feasible solution. So, and we do need the equals because the pKVM should execute the confidential VMs well, and the only way to communicate is through equals. And then the supervisor binary interface confidential VM extensions is a standard in the RISC-V community that tries to provide a common set of equal ABI for all the possible hypervisors. So regardless of what you run on either side, you can mix and match, like you can run KVM on any other RISC-V hypervisor, and similarly the other way around. So it provides equals to configure launch and manage virtual machines, and also the equals to attest and the guest, and let the guest tell which pages are shared and which interrupts are allowed. But this project is still not finished, and we would like your feedback on what is really necessary and how to design the best interface, because we're mostly copying ARM, and well, it might be with all the mistakes that ARM has made as well. So it would be good to actually gather the feedback, and well, there is also a work in progress on device assignment and migration, and it would be good to know if it is actually necessary to have it in the early stages, or we can have the confidential virtual machines be useful even without that. So how does the pKVM fit into this code? You can see here that there's an HS mode, and it has TSM, which takes care of context switching, nested virtualization for the H extension. And pKVM would be an implementation of the TSM for Cove. So it would communicate with the host MM, which would be Linux in this case, through the Cove H ABI. This would give the interoperability. But the main advantage of pKVM on ARM was that as pKVM and Linux start as the same binary, like the interface between them is basically just an internal API. You don't really mix and match different versions of Linux and pKVM. So having a stable interface there can also bring problems in case you want to fix something fast. And well, then it takes a year at least to push the standards through the RISC-V process. And if it was just a dynamic interface, you could do it basically a patch, quick patch on the second day, have both pKVM and KVM communicating through a new interface without any problems due to compatibility, because it's still like one binary that communicates with itself. So it's possible that even if the Cove H ABI is there, we will diverge, and then it's going to also cause problems with interoperability. So we would like to make sure that the Cove H ABI is as good as possible. So the Cove tries to do the confidential VMs. It doesn't do anything else. So you can't run non-confidential VMs. And still there's some corner cases for the confidentiality, because, for example, the host can see what MMIO the guest uses. And well, the guest first chooses the pages which are MMIO, but then if it accesses them through different instructions, the host sees the instruction, and the instruction also encodes which register it is. So it could share some information about the internal operation of the guest. And like the hypervisor doesn't have to implement it like this. So for example, pKVM is always translating the accessed instruction to be the same, but it's not standardized. So it's something we might want to fix if you think it's important. And then there's the second stage page faults, because the confidential guest is given some parts of it gets physical memory. And well, if it tries to access something else, it results in violation. And currently the standard says that, well, even though the guest should have accessed it, the host might be interested, but it could also be triggered by some bugs. And well, we don't probably want to know even if the guest is buggy. So that's another question for guest timer, because now when the guest goes to sleep, it's like waiting for interrupt. A timer might be one of the first interrupts that it arrives. And the current specification says that the host is told when the guest timer interrupt is being injected. So it technically allows the better utilization of the CPU, because then you don't have to schedule a waiting guest, but it also provides some information back about what the guest is doing, as HR timers are going to use this. And then the equals are also undefined in the code, because you can't really describe what the guest does and what the host sees from it. So most of the equals should stay in the pKVM, and it's only those like writing to console that really need to go to the host. But that's also an open question how to define this. And another point of contention is that while the guest currently can control which interrupts are able to be injected, and the host isn't able to inject any other interrupt that the guest is allowed, if we do implement the assigned devices, then the RISC-V MMIO doesn't allow this amount of control. So there would be kind of a disconnect between having a physical device assigned to a guest that can inject anything, and if the device isn't really that trusted, it would be basically the same as host injecting the interrupts, but we don't allow it, so that would be weird. And just for a high-level overview how the equals are going to be used, it's the VS host that triggers an equal. In this case, let's say it's set up the protected VM, and then it's called pKVM vCPU run. The pKVM in the HS mode receives a trap. It starts executing the handler. It sees, oh, it's an equal, and it's an equal for pKVM. So the pKVM code runs, sets up the VS guest, and then enters it. And this is very similar to how on RISC-V even the KVM works with its user space. So if you put, instead of VS host, you put HUQM or RISC-VMM, and then there's HS KVM and VS guest, it would basically go through the same code path. Like still the guest would do what it does. It could do equal that's handled in pKVM or KVM, and if it's MMIO, it would go back to the host or user space. And this was an idea I had. So, well, it's basically the same as what KVM does. So let's try to reuse as much of KVM as possible. And well, it didn't turn out to be so easy, because first, KVM is using a lot of infrastructure of kernel that has far-reaching global data structures. So like you can easily say, well, KVM is using mem slots for this, but well, then the mem slots, they depend on the MMU and MM structures in kernel. And so then, well, yeah, let's take this MM structures, but then the dependencies went so far that I actually had to give up and say, well, I don't trust this model anymore. The reusability of code is a nice idea, but I guess it's not that easy to actually have a small and contained part. And again, then it would also be more fragile, as changes to the generic kernel code would affect pKVM. And well, pKVM tries to be a trusted hypervisor, and it would, if there were too many changes, it wouldn't be as easy to trust. So I think that minimizing the amount of shared code might be beneficial for the confidentiality and the trustability of the hypervisor like pKVM. And there's still the KVM code that can at least get somehow reused. It's for managing the guest, setting up the second stage page tables, just configuring the HCSRs. That one doesn't have as many far-reaching dependencies, but it's still, there's basically nothing that can be reused without refactoring, as at the end there usually is a call to a global structure that needs to be threaded out of it and make it, for example, the memory that it uses to actually get loaded as an input to the chain and not somehow global taken from a global structure as very deep in the call stack. And generic kernel code, there's even less of it. Like we could use the spin locks, and well, that's probably all that pKVM does now. I don't know if there's more. So the more interesting code reuse possibility is between architectures, because now that we have pKVM on ARM, we plan to do pKVM on RISC-V. There's also x86 pKVM somehow in the works, and we could do the same as KVM does for its user space interfaces, which is to split them into the word and the architectural parts. Here, because, for example, memory is basically just an array of bytes and some radix tree on top of it, it could be made somehow common code for it more easily, and it would still be just a part of the trusted hypervisor parts just for all architectures. And when we have this, we could also define a common ABI, which all the architectures would use, just through slightly different hypercall mechanisms, although that leads to a bit of a conflict with the COV, because RISC-V is dead set on the COV, so all the other architectures would probably have to adopt it, which is another reason why it would be good to have COV there, or just drop this idea totally and go for Rust, because pKVM, its own separate binary, basically that just Linux carries, and it gets loaded and executed completely in isolated mode. So the only interface that it uses is through architectural isolation boundaries. And it's similar to learning a completely different language in your user mode. So now that we even have seen that the code reuse between the C Linux isn't that easy, we could, when we're already rewriting it in C, we could just rewrite it in a language that has a type system that has actually some expressibility. So I think it would be a nice project, though I haven't really started working on trying to do this in Rust, as there's another possibility, as there's something always coming in RISC-V, and the next extension that also changes the confidential VMs quite a bit is supervisor domains. It does not add new privilege levels, so we still have the M, HS, VS, and BU, but it gives the M mode the ability to now run multiple S modes or HS modes here through a next layer of page tables. And well, these page tables, they don't virtualize, so there is no address remapping. You just get the page table granularity, which is 4 kilobytes, to isolate the S modes. And you also get a bunch of state registers to properly isolate the state. And the IMMU has similar third stage. And with this, the general model that's expected in COV is that there's a the security manager running in HS mode next to Linux also running in HS mode. But currently, the plan is to have basically the T be a part of the firmware. So it's not as easy to update as Linux. But these extensions for the supervisor domains, they can also allow you to just create your own supervisor domain. So Linux could tell the firmware to, well, run this binary, which would be pKVM, but not really, and run this binary in a supervisor domain. The advantage is that for first, Linux still runs in HS mode, so it can run the non-confidential VMs with the acceleration of the H extension, because with pKVM, you had to do nesting, and well, that's not ideal for performance. And another benefit is that the supervisor domain, the only code that ever executed it is the trusted hypervisor. So the attestation would be much simpler, because currently with the pKVM code, all the Linux code executes. So you still have to trust that the Linux doesn't do anything shady before it is deprivileged. And another flexibility is that, well, you executed one trusted hypervisor in HS mode, and well, then the Linux could execute just as well another second domain. So you could have multiple supervisor domain hypervisors that give you a different security or trust guarantees depending on what you need. Well, but these extensions, they're not even yet ratified, so it will take the hardware quite a long time to implement them. And so in conclusion, like, we can do pKVM on RISC-V, and we would really like to do it with the Cove ABI to have the unified communication channel between all possible hypervisors and their supervisor counterparts. And well, while the code reuse is technically possible, it definitely is not simple. So it's something to consider, that writing it anew might be the best solution. And thank you. And there are some topics that I would like to discuss, because most of this presentation, the purpose is to gather more of the feedback, as RISC-V is still not here yet. And we would like to avoid making the same mistakes that probably you are dealing with on a daily basis. So if you have any strong opinions on any of these topics, I'm more than welcome to hear them. And now the room is yours. The question was whether I was able to test on any actual hardware. Well, the only hardware I use, or the only implementation I use, is QEMU. So no. I only heard that the Hi-Fi P550 is supposed to have some extensions, but they don't even market it. So it was botched probably. I don't know how much, and I don't have access to the hardware either, because, well, I didn't want to get it if it's not H. Mm-hmm. Mm-hmm. Yeah, it was probably not a question, just suggestion that we should have a live update of both pKVM and an overlaying hypervisor while the guest VMs are running, which definitely is possible, because just how you executed the Linux into VS mode from pKVM, you can then go back and have the Linux kexec, and then it would be kind of awkward to kexec the pKVM, because you would need to make sure that the new hypervisor isn't something that's inappropriate. So maybe there would need to be an interface if the guests agree that this is possible, because that would be something to implement, I guess, in the call API, to first ask the guest if like they approve, because now, but yeah, PKVM is fine. Okay. Okay. The new version, yeah, this definitely is possible. Like it would be just kexec on for 2 softwares. So it's a good suggestion. I will bring it up. Excuse me. Okay. I think that might be better suited for the like supervisor domain, maybe, because here it would be kind of more isolated already. So you would just, you don't care what the Linux does. It can exec as much as it can, and then you can create the supervisor domain and maybe convert the VMs between them. So yeah, we'll see how this goes. So I guess we can all go and eat. Thank you for your attention.